The strength of the U.S. military comes not only from missiles or aircraft carriers, but from the logistics machine that feeds millions of service members every day. A food system worth more than $20 billion per year, quietly operating to keep the world's largest military force constantly ready for combat. So what happens behind the scenes when every meal must cross oceans, deserts, and battle lines to reach soldiers precisely on time? That journey begins with tightly controlled food sources, moves through a multi-layered military logistics network, and then enters military kitchens that operate like industrial production lines. It is followed by a closed-loop inspection and distribution process, where even the smallest error can affect discipline, health, and the combat readiness of an entire unit. Today, let's follow Agriculture Insight as we trace the journey behind a U.S. military meal, where the food industry, logistics, and national security connect to form the silent foundation of a massive warfighting machine. On average, each military academy with more than 4,000 cadets must serve between 10,000 and 13,000 meals per day. In that environment, there is no concept of delay or improvisation. A demanding training schedule allows each cadet only 15 to 20 minutes to eat. Even the slightest disruption immediately triggers strict dining hall discipline. Behind every meal lies a rigorous selection process. Those working in the kitchen need more than culinary skill. They must pass background checks, moral and medical evaluations, along with dozens to hundreds of high-pressure assessments. In the military, the kitchen is part of the security logistics chain, and the cook is a strategic link in maintaining discipline. For that reason, military meals are not prepared for indulgence, but for control of the body. Salt levels are carefully calculated to prevent excessive thirst, limiting water intake and bathroom breaks, factors that could interrupt movement or expose positions. In emergency situations, even aroma is minimized, as scent itself can be detected. Here, seasoning serves not taste, but survival and security. Because every meal is directly tied to discipline and security, any error is eliminated at the earliest stage of the operational chain. From 5 a.m., before anyone steps into the kitchen, before a single pot is set on the flame, the first battle of a military meal begins with the ingredients. Preparing food for a military dining facility is no different from a covert logistics operation. Every kilogram is precisely calculated, refrigerated containers are hoisted straight onto ship decks, forklifts move in fixed formations, where logistics operates like a silent tactical mission. And from this logistics line, the ingredients move straight into the first kitchen of the military meal production facility, the vegetable and fruit prep station. Here, every portion begins to be standardized for large-scale service, with one single objective: on time, absolutely safe, and completely uniform. Fruits such as pineapple, watermelon, cantaloupe, and kiwi are processed on specialized stainless steel tables, peeled, cubed, and rapidly chilled to preserve freshness, ready for fruit salads or side dishes and standard meal sets. For vegetable salads, the requirements are even stricter. Greens are not chosen for delicate flavor, but for their ability to withstand the pressure of a military kitchen. That is why lettuce and cabbage are always prioritized. They pass through multi-stage washing systems with circulating cold water, then are sorted for different types of salads. In a military meal, vegetables typically account for about 25 to 30% of the portion. Not because soldiers prefer eating greens, but because they need them to meet nutritional requirements. As the trays of salad are placed into cold storage, the soldier's meal enters its decisive stage. The kitchen immediately shifts tempo, transforming into a high-pressure production line where hot main dishes are handled with industrial-scale equipment and time is measured down to the minute. Every movement must be absolutely precise, because this is the direct source of energy for the mission ahead. In military kitchens, meat is selected for stability rather than tenderness or rich flavor. Lean cuts with firm muscle structure are prioritized because they maintain their shape when cooked in large quantities and remain consistent even after multiple reheating cycles. Next, meat is rarely brought straight into the kitchen in a fresh state. Instead, it is deep chilled to below 2 degrees Celsius to control microbial growth and synchronize preparation timing for thousands of servings. In a demanding training environment, even a single batch of meat that turns out too dry or too tough can noticeably affect soldiers' morale. At the same time, the cutting process does not rely on human judgment, but on precision machinery to ensure that each portion delivers equivalent nutritional value. Every day, this system processes approximately 20 tons of meat, meaning that even a minor mistake at the prep stage can disrupt the entire production line and impact training schedules and mission readiness. In a military kitchen, steak is a cold but intelligent operational equation, where every decision serves the goal of feeding troops safely and on time. First, the meat is selected according to 3 clear criteria: stability, ease of control, and the ability to withstand large-scale cooking. Next, the thawing process takes place slowly over 60 minutes, helping preserve the muscle fiber structure while keeping microbial activity at the lowest possible level. The seasoning stage is then kept minimal, using only salt and basic spices because uniformity matters more than individual flavor when serving an entire unit. At the same time, steak in military kitchens is always cooked thoroughly, using industrial ovens or rapid searing methods, prioritizing absolute safety over culinary preference. The concept of medium rare has no place here, as the military does not accept even the smallest risk. Buffalo chicken becomes a rare exception, not because it is more luxurious than other dishes, but because it serves as a disguised morale booster for soldiers. This dish does not appear frequently, usually only about once a month, just enough to create a sense of novelty without disrupting nutritional discipline. And even when it does appear, military buffalo chicken is not the same as its civilian counterpart. The chicken is carefully pre-processed, then may be quickly fried to form a light crust, but is mostly oven-baked or steamed and finished on industrial griddles to ensure food safety at scale and maintain structure after hours of heat holding. The original version is rich in butter and heavy heat, but in the military, butter is significantly reduced to prevent heaviness, digestive discomfort, and interference with high-intensity physical activity, keeping the calorie count at around 450 per serving. The result is a dish that sounds indulgent, yet is calculated like everything else in the military. Familiar enough to lift morale, controlled enough to pose no risk. Buffalo chicken here is not meant to please the palate, but to remind soldiers that even within steel discipline, there are still moments that feel human. In military kitchens, pasta is the line saver when meat or vegetables run into problems, but the way it is prepared is anything but random. The noodles are boiled slightly softer than usual from the start to ensure microbial safety when serving large quantities under unstable conditions. They are then drained and kept warm, ready for assembly. At the same time, tomato sauce is prepared separately in high-capacity kettles, seasoned with strict restraint on salt and almost no monosodium glutamate, to avoid triggering thirst, since soldiers' water intake is always regulated. When it is time to serve, the pasta and sauce are combined or ladled together according to standardized portions. The technical preparation time for pasta is typically 3 times shorter than for other dishes, making it a flexible option when the kitchen line needs rapid adjustment. The result is not a delicious pasta dish, but one that is stable, safe, and provides sufficient energy to keep the entire unit operating on rhythm. Beyond pasta, sausages are not merely a convenient food. They are a kitchen contingency solution. When the main dish plan runs into trouble, sausages can be plated quickly, while still providing sufficient energy for the entire unit. For that reason, many military kitchens do not rely entirely on prepackaged products, but produce sausages in-house under internal standards to maintain control over quality and service tempo. The cook begins with chilled ground meat, then blends it with seasonings according to a fixed formula to ensure uniformity across production batches. The mixture is stuffed into casings, filled evenly to prevent air pockets, and twisted into precisely measured lengths. Because ground meat is considered high risk, temperature, timing, and hygiene are monitored with extreme strictness. Even a minor deviation can require the entire batch to be discarded. At mealtime, the sausages are grilled or seared for color, then placed directly into hot dogs or served on meal trays. A large kitchen can process around 1,000 sausages in a single shift, enough to bring the entire production line back on rhythm. Once thoroughly cleaned, the potatoes are boiled in water until fully cooked. This method allows each tuber to cook evenly from the inside out without becoming mushy or losing its structure. They are then transferred to high-capacity industrial mashers, where they are blended into a smooth, uniform consistency with precisely measured seasoning, enough to provide flavor without causing heaviness or excessive thirst during high-intensity physical activity. Each day, a military kitchen can process up to 5 tons of potatoes, equivalent to roughly 40,000 portions served consistently and on schedule. Thanks to their ability to retain heat, resist drying out, and remain easy to digest, mashed potatoes become the quiet backbone of the meal tray. A simple dish, yet resilient enough to sustain the energy rhythm of an entire unit throughout a full day of training. Fish is a primary source of omega-3 fatty acids, EPA and DHA, nutrients that are nearly absent in red meat. These fatty acids help reduce muscle inflammation after high-intensity physical activity, support joint recovery, and are especially important for neurological function, maintaining focus, reaction speed, and emotional stability under prolonged stress. In sleep-deprived training environments, omega-3s also help limit cognitive decline and slowed response times, factors that could lead to tactical errors. In the military, eating safety is just as critical as nutrition. In the past, serious incidents have occurred due to choking on fish bones, which is why fish selection and processing are strictly controlled. Varieties such as cod, salmon, and pollock are preferred for their firm texture, minimal small bones, and suitability for large-scale preparation. The fish is carefully filleted, then typically fried until crisp or pan-seared for 10 to 15 minutes to maintain structural stability and reduce risk when consumed quickly during tight service windows. On the tray, fish is paired with salad or steamed vegetables to maintain nutritional balance. In the bakery section of a military kitchen, scale and precision are prioritized above all else. Not for display, but for operational stability. Every hour, thousands of soft bread rolls, simple pastries, and nutritional biscuits can be produced. Familiar items that are easy to store and well-suited to large-scale rations. Rather than elaborate, decorative baked goods, the kitchen focuses on white bread, whole grain bread, and low-cream pastries to ensure longer satiety and easier digestion. Every autumn, nearly 3.4 million metric tons of apples pour into Washington, a large portion of which consists of utility-grade apples. Not beautiful enough for store shelves, yet perfectly crisp and sweet, making them the golden ingredient for surprisingly rich and flavorful juice batches. Before processing, the apples are moved into massive recirculating water tanks, where a combination of aeration and dilute chlorine is used to knock off dirt and impurities. The cleansing process then continues with high-pressure water jets, which meticulously scrub every small crevice on the skin. After the rigorous cleaning process is complete, the fresh apples are transferred onto a dewatering conveyor system. Here, they pass through a system of rotating and vibrating rollers, which helps completely drain the surface water. This process is often combined with a gentle stream of warm air to ensure the apples are dried most effectively without compromising the quality of the fruit. Next, the apple mill operates as a cell disruption chamber. Inside, a rotating shaft is fitted with dozens of high-speed cutting blades or crushing hammers. As apples drop in, centrifugal force presses them against a stainless steel sieve, simultaneously crushing them and controlling the particle size. This specific design helps preserve the apple's full flavor without any metallic off-taste from rusty steel, minimizes heat generation, and protects the natural enzymes before pressing. Thanks to the intense pressure from a high-capacity screw press system, all the liquid is extracted from the mash. However, to achieve industrial-grade clarity, the decisive step is microfiltration using stainless steel pipes. At this stage, only small molecules like water and sugar can pass through. Up to 99% of microorganisms, enzymes, and colloidal particles are securely trapped on the surface. But did you know that the 100% juice label on apple juices today doesn't necessarily mean they are pressed entirely from fresh apples? Many products are actually reconstituted concentrates, or even blended with grape or pear juice to lower costs. Therefore, every drop of original, unadulterated apple juice is not only distinct in flavor, but also reflects a level of honesty that not every production line dares to uphold. In Mexico, aloe vera is an ingredient famous for its strict requirements regarding processing speed. From the moment it is cut from the field, the aloe must complete the entire processing stage in under 4 hours. Any delay will cause the enzymes in the leaves to spontaneously activate a degradation process, resulting in the gel turning brown and significantly reducing its biological activity. Starting this race against time, the leaves are moved straight to the production line, cleaned, and then dipped into a surface stabilization tank. This step is not merely soaking in water. It effectively creates an environment for immediate oxidation inhibition, helping keep the gel clear and slowing down decomposition. But to me, the most fascinating stage must be the cutting and filleting of the aloe flesh, as this step demands swiftness and the precise skill of material sensing, down to the millimeter. The aloe gel does not cling tightly to the rind but slides on an extremely thin layer of cells, only a few tens of micrometers thick. Therefore, the worker must simultaneously handle 3 key factors: positioning the knife close to the rind, maintaining an absolutely stable cutting angle, and controlling the knife's force, strong enough to fully separate the entire gel block, yet delicate enough not to pierce the flesh, containing all the expensive active compounds unique to aloe vera. Only the purest gel, which retains its biological structure and natural viscosity, is channeled into the extraction line for making gel or beverages. However, not everyone knows. Aloe vera products should ideally be consumed within a maximum of 1 to 3 months from the date of manufacture, because the longer they are stored, the more sharply the biological compounds decrease. Beverages can ferment, and gels will oxidize, even if their appearance remains completely normal. Before becoming a sweet icon, the journey of the strawberry begins in the temperate fields of California, where farmers spend more than 6 months of continuous care before harvesting the first crop. Workers use small tipped knives to remove the stem along the contour of the calyx, avoiding the white flesh inside, which bruises easily. Damaged berries are then discarded, since even a single bruised fruit in a batch can alter the flavor of the whole batch of jam and cause it to discolor more quickly. The next step is ultra-fast freezing at temperatures dozens of degrees below zero. This step is costly because it requires high-capacity freezing chambers running continuously, but in return, it is the key condition that allows all the water to crystallize into tiny ice crystals, helping lock in the bright red color, the sweet-tart balance, and the fibrous structure. The strawberries are thawed slowly to prevent breakage, then cooked at a temperature below boiling. This heat is enough to concentrate the sugars without destroying the organic acids and aromatic essential oils, the elements that create the true strawberry flavor. During cooking, the sugar gradually seeps into each layer of fruit, giving the jam a supple, glossy texture while still preserving the visible strands of fruit, completely different from jams made with gelatin, which have a uniform, depthless structure. When the jam reaches the ideal consistency, it is poured into glass jars and sealed with tin lids while still hot. The tin lids are not just aesthetic. Once tightened, they create an almost vacuum-like environment that prevents microbial intrusion without the need for preservatives, and they do not react with fruit acids, so the aroma and flavor remain intact over time. With this rigorous process, in Europe alone, where annual strawberry jam consumption reaches up to 480,000 tons, whole fruit strawberry jam has become so popular that nearly every household keeps a jar in the kitchen. Right after sugarcane juice leaves the press, it still contains fibers, dust, and tiny organic compounds, impurities invisible to the naked eye. For this reason, a very small amount of lime is added to pull all impurities down to the bottom. This reaction works much like the clarification process used in Heineken's beer, or the clarification of Tropicana's fruit juice, using a chemical agent to bind and coagulate impurities, allowing the sugarcane juice to become crystal clear and ready for the concentration stage. As the juice passes through a multi-stage evaporator system, only the water disappears. The sugars gradually thicken into a golden syrup. Most major brands invest heavily in this stage, because the evaporation rate and vacuum level directly determine the color, aroma, and stability of the final sugar. In the crystallization phase, seed sugar crystals are added as initial nuclei for the solution to cling to, gradually growing into well-defined crystals. The formation of the first sugar grains is similar to the way sea salt or crystal glass is cultivated, a single guiding crystal for the entire batch. Once crystallized, the mixture enters a centrifuge, where the crystals are separated from the molasses. Raw golden sugar retains 3 to 5% cane molasses, giving it a natural caramel aroma, while refined white sugar reaches 99.9% sucrose, precisely the purity level required by confectionery companies to ensure consistent flavor across millions of products. Even after centrifugation, the crystals remain slightly moist and prone to clumping, so they are dried to an optimal moisture level. For segments requiring absolute whiteness, such as sugar used for marshmallows or fondant, the crystals are even redissolved, filtered through multiple layers of materials, and centrifuged again to eliminate any remaining pigments. The final result is pure white sugar granules, so uniform that they look almost identical. But here's the interesting part: they were never truly identical. Natural variation between crystals is merely minimized through controlled crystallization and industrial grading systems, making them appear perfectly consistent to the human eye. Tomato sauce is among the most widely consumed vegetable-based products in the world, thanks to its limitless versatility. It appears in thousands of culinary recipes, but few people know that behind a seemingly simple bottle of sauce lies an entire industry operating under global standards. The journey begins when tens of tons of tomatoes are unloaded onto the factory's receiving conveyor to enter the washing stage. Here, the flume water system is considered the international standard. Water is pushed into a gentle, controlled current, strong enough to sweep away impurities, yet soft enough not to bruise the extremely delicate flesh. For tomato sauce, factories often prioritize the hot break method, rapidly heating the crushed tomatoes to a very high temperature to deactivate enzymes and preserve a stable thickness. The tomatoes are fed into industrial grinders, where steel blades turn them into a fine puree. Immediately afterward, the mixture is passed through sieves and membranes to remove seeds and skins, an essential step that ensures a smooth sauce, stable color, and long shelf life. The tomato puree is cooked in steam-jacketed steel kettles, stirred continuously to prevent burning. Meanwhile, onions and garlic are sautéed in sunflower oil. On average, a 1,000-liter batch of tomato sauce requires about 9 kilograms of onions and garlic before being blended with the tomato puree, along with salt, sugar, spices, and vinegar. For peanut butter, the process begins with shelled peanuts going straight into industrial roasters for 25 to 30 minutes. The temperature is automatically programmed to rise in stages, so the nuts dry evenly from the inside out. Once properly roasted, the peanuts pass through a soft shell removal system. Compressed air loosens the thin skins, and rollers separate the kernels without cracking them. A vibrating conveyor and suction fans remove the leftover flakes before an optical sorter scans up to 7,000 nuts per minute to eliminate burnt, unripe, or defective ones. Only the qualified peanuts move on to be ground by high-speed rotating mills, breaking down the protein oil structure to form a smooth, golden paste. At this stage, salt, sugar, or vegetable oil is added through precision dosing systems accurate to the gram. The mixture is then heated in a closed cooking chamber to achieve the ideal consistency and gently pasteurized to extend shelf life while preserving the roasted peanut flavor. The hot peanut butter is then filled into jars ranging from 250 grams to 1 kilogram, sealed in a sterile environment, rapidly cooled to stabilize its texture, labeled, and sent through a final inspection using cameras and weight sensors. In the past, farmers had to carry baskets, bend their backs to lift each melon weighing over 2 kilograms, and haul them across long rows under the blazing sun. A grueling task that drained their strength and often left the fruit scratched before it even reached the truck. Today, they have the help of mobile harvesting conveyors, a smart, mechanical arm designed specifically for melons. The belts are made of soft rubber, allowing workers to gently toss the fruit onto them without damaging the rind. One end of the conveyor lies close to the ground to receive the melons, while the other end rises to deliver them directly into the truck bed. 2 conveyors operate side by side, moving slowly between the rows. Around 20 workers coordinate seamlessly along the system, forming an open-air assembly line. Pickers, placers, and loaders working in perfect rhythm. The conveyor doesn't replace human hands, but it reduces over 70% of the heavy lifting, cuts harvest time in half, and ensures every melon remains intact and gleaming under the golden sun of the season. The John Deere combine harvesters are considered the backbone of American mechanized agriculture. Powerful, multi-purpose machines capable of harvesting everything from wheat, corn, and soybeans to sorghum, simply by changing the front header attachment. When the sorghum fields of America's Midwest turn a deep crimson red, these giant combines begin to roll. At the front, a 10-meter wide cutting header glides just above the ground, feeding the entire stalk into the processing chamber, where high-speed rotors and strong airflows separate the grain from the stalk before lifting it into the grain tank above. This front section, known as the header, is built as a modular unit that can be swapped depending on the crop. For corn, the header uses deep row grabbers designed to pull and cut tough stalks. For sorghum or wheat, it's replaced with a draper header, a flat cutting platform with a moving belt that smoothly feeds each stalk into the threshing system with precision. Sorghum may not be a common sight on the dinner table, but it's one of the most resilient and vital crops on Earth. Grown widely across Kansas, Texas, and Oklahoma, it thrives in dry, scorching lands where few other plants can survive. In your kitchen, spring onions are a familiar ingredient. But have you ever wondered how they're harvested across fields that stretch for dozens of hectares? Let's visit Denmark, the birthplace of Asa Lift, the pioneer of Europe's vegetable harvesting technology. At the front, a thin steel blade slices just below the roots, while rubber rollers gently grip the stalks and lift them from the soil. Next, an angled conveyor belt carries the onions upward, where soft rotating brushes remove dirt before neatly stacking them into crates. In just 5 minutes, a single machine can harvest over 600 meters of onion rows, up to 20 times faster than manual labor, while keeping every stalk straight, clean, and perfectly intact, ready for its journey to your local supermarket. During the bright summer months in Florida and Mexico, mango orchards reach their harvest peak when millions of golden fruits ripen at once, filling the air with their fragrance. Hand-picking remains the preferred and almost indispensable method, since each mango variety ripens differently and has a unique skin texture. Pickers must observe the color, feel the firmness, and check the stem to determine the perfect time to harvest. Low-hanging fruits are picked directly, while those high above are reached using hydraulic lifting baskets, compact in appearance but capable of extending up to 8 to 10 meters high. The platform is controlled by a small panel on the handrail, allowing pickers to raise, lower, or rotate the lift with just a few simple moves. This system boosts productivity up to 5 times compared to ladders, ensures worker safety, and protects branches from damage. After harvesting, mangoes are rinsed under gentle water jets or immersed in circulating wash tanks to remove sap and dust, then dried, sorted, and cold-packed for export. Every year, Mexico, the largest mango exporter in the Americas, supplies over 2 million tons of fresh mangoes to global markets, most of them still picked carefully by hand from orchards like these. The tree shaker is the secret weapon of America's plum orchards. Its steel arm clamps tightly around the trunk, then shakes it powerfully for a few seconds, at a frequency of up to 400 vibrations per second, causing thousands of ripe plums to rain down onto large catching tarps without damaging branches or unripe fruit. In just a few short seconds, a tree is completely harvested. From the tarps, the plums are moved directly onto conveyor belts, passing through cleaning, sorting, and packing stations right in the field. Each shaker can harvest up to 60 tons of plums per day, operating tirelessly under the summer sun. Alongside the trunk-shaking tree shakers, American farmers also use another type of machine designed for low, narrow canopy plum orchards: the canopy shaker. Its 2 symmetrical rotor arms vibrate at a frequency of 6 to 10 Hz, sending oscillations directly through the canopy to shake off ripe fruit without breaking branches. Beneath the trees, a closed system of catching tarps and conveyors collects the falling plums, separates leaves and debris, and transfers the clean fruit straight into storage bins. Leaving behind America and Europe, we arrive in South Korea, where the lowering of pond temperatures below 10 degrees Celsius marks the beginning of the lotus root harvest season. Harvesters wear full-body waterproof suits, thick rubber gloves, and use broad, blunt-tipped knives, tools that allow them to cut and separate rhizomes without cracking their delicate skin. Hidden beneath a thick layer of mud, each lotus stem contains 3 to 6 connected root segments, crisp, starchy, yet so fragile that even a slight touch can cause them to split. Instead of digging with shovels, farmers use high-pressure water jets to loosen the soil and gently release the roots without any mechanical impact. Once freed, the roots float to the surface, where workers gather them into wooden boats, then lift them ashore with small cranes. The process must be quick. Within just 2 to 3 hours of air exposure, the roots begin to oxidize and turn brown. Thanks to this delicate and precise technique, South Korea exports over $100 million USD worth of lotus roots each year, turning a plant born from the mud into a high-value agricultural product on the global market. When aloe vera leaves reach full maturity, about 8 to 12 months old and nearly 80 centimeters long, farmers begin harvesting. Using sharp knives, they cut each leaf close to the base, then tilt the cut end downward to drain the yellow sap containing aloin, a bitter compound that can ruin an entire batch of gel if not removed properly. Harvesting aloe requires speed and precision, as even a small bend or bruise can cause the inner gel to oxidize. Only thick, plump, unbroken leaves are considered suitable, and they are carefully placed into shallow trays or soft-lined crates to protect their delicate outer skin. On large farms, mobile harvesting conveyors run along the rows, collecting hundreds of leaves in just a few minutes, reducing manual labor by up to 70% while keeping the gel inside fresh and intact. Typically, a skilled worker can cut up to 1,000 leaves per day, but ensuring that each leaf remains firm, clean, and free of yellow sap still depends entirely on the harvester's experience. The key to the purity of every drop of aloe gel that follows. The grapefruit harvest begins when the fruit turns a uniform shade of pinkish gold, with taut, slightly textured skin. During peak season in Texas, the homeland of the famous Rio Red variety, skilled pickers gently twist each fruit along the stem, creating just enough torque for it to detach naturally without tearing the peel. But under the dry, scorching sun of the semi-desert region, time is the greatest enemy of quality. Just a few hours delay after full ripeness can cause the skin to dull, essential oils to evaporate, and the flesh to begin drying out. That's why the entire harvest must be fast, continuous, and precise, ensuring that every grapefruit, the moment it leaves the branch, still retains its glossy, aromatic skin and the signature sweet tart flavor that has made Rio Red a beloved name across the United States. In the summer months, when rows of zucchini fields in France reach peak production, hundreds of workers head out for the biggest harvest of the year. Despite advances in mechanization, zucchini are still picked almost entirely by hand, as their thin skin and soft stems make them extremely prone to scratches and bruising. In the fields, pickers move along each row, holding the fruit with one hand and using a small knife to cut the stem cleanly with the other, making quick, precise movements to avoid tearing the glossy green skin. Each worker carries a shallow plastic crate, which, once full, is emptied onto collection trucks, moving slowly alongside the rows. To preserve freshness, harvesting takes place every 2 to 3 days, when the fruits reach about 18 to 20 centimeters in length, the golden stage for flavor and yield. On average, a skilled picker can harvest 400 to 600 kilograms per day, all done in the early morning hours when the air is cool and the fruits are still firm, vibrant, and full of life. Next, let's visit the shaded cocoa plantations of southern Ghana, the birthplace of the chocolate bars you know so well. The harvest season begins with the rhythmic sound of machetes striking through the forest, a sound locals affectionately call go-to, the signal that the golden season has arrived. When the cocoa pods turn deep red or golden yellow, pickers use curved machetes to cut them from the stem and gather them into small piles beneath the trees. There, they split open the pods and remove the ivory-colored beans, wrapped in a sweet mucilaginous pulp. This pulp is what undergoes natural fermentation for 5 to 7 days, during which enzymes break down sugars and acids, releasing hundreds of precursor aroma compounds. Surprisingly, 60 to 70% of chocolate's final flavor is formed at this stage, long before the beans are roasted. Yet, despite the meticulous labor of millions of farmers, cocoa growers earn less than 2% of the final value of the global chocolate industry, while most profits go to processing giants in Europe and North America, where these humble beans are turned into the sweet indulgence that many of their growers have never even tasted. On average, a farm in the United States spans several hundred acres. But in major grain belts, such as Iowa and Nebraska, farm sizes often surge to around 2,500 acres, equivalent to nearly 2,000 football fields combined. As a result, efficiency at this massive scale becomes an unforgiving challenge. A steering deviation of just a few inches can waste tons of seeds due to overlapping rows, or cause heavy machinery to crush crops that are already growing. This is why many large farms in the United States have now transitioned to GPS RTK technology, one of the key innovations propelling the country directly into the era of precision agriculture. At its core, while conventional GPS positioning operates with errors of several meters, RTK in the US follows a fundamentally different principle. The technology relies on fixed ground-based reference stations to measure and eliminate satellite signal disturbances, continuously transmitting real-time correction data to tractors in the field. As a result, errors caused by atmospheric interference or satellite clock drift are effectively removed, reducing positioning accuracy from arm-length margins to just over 1 centimeter, roughly the width of a fingertip, across enormous fields. Thanks to this technology, a bulky tractor can now operate like a true robot. It not only eliminates overlapping seeding, but can also return precisely to the same wheel tracks from previous seasons, an advantage that helps reduce input costs and protects soil structure from excessive compaction caused by new tire paths. With upfront investments of at least $10,000 USD per unit, along with annual signal subscription fees, RTK has become a mandatory expense for maintaining competitiveness in large-scale agriculture. For decades, American farmers have been trapped in a vicious cycle. Weeds grow increasingly resistant to herbicides, forcing higher chemical dosages that degrade soil structure and trigger consumer backlash. As environmental regulations tighten, carbon robotics introduced a game-changing solution: the laser-powered weed-killing robot. This machine is essentially a mobile supercomputer fused with heavy industrial mechanics. As it moves across the field, a system of 30 industrial cameras continuously scans the ground. Within milliseconds, an AI processor analyzes the data and isolates targets, smart enough to distinguish young crop seedlings from weeds, even when they grow intertwined. Once a target is confirmed, high-power laser units fire ultra-short thermal pulses directly at the weed's growth point. Weed cells are destroyed instantly, without heating the soil or touching a single leaf of the crop. With a processing speed of up to 100,000 weeds per hour, a single machine can replace the labor of a 50-person workforce. However, the biggest barrier to adoption is its price tag, up to 1.4 million USD, a risky investment without sufficient scale. Yet for farms spanning thousands of acres, the robot's ability to operate continuously through the night becomes the decisive advantage in the race against time. As chemical and labor costs continue to rise, this robotic system not only enables cost recovery within 2 to 3 growing seasons, but also opens a viable path toward large-scale clean agricultural production, something that was previously considered impossible. Beyond leading the world in tractor production, the United States dominates more than 40% of the global market for smart agricultural equipment. With over 450,000 combine harvesters currently in operation, the U.S. runs one of the largest harvesting systems on the planet, structured around strategic grain crops such as corn, soybeans, and wheat. Yet the true advantage lies not in sheer scale, but in how these machines optimize themselves while working. High-capacity harvesters from John Deere and Case IH, the two pillars dominating the North American large harvester segment, employ automated axial threshing systems driven by algorithms. As the machine operates, onboard systems continuously analyze grain flow, moisture levels, and loss signals, automatically adjusting concave clearances and airflow in real time. This keeps harvest losses at the lowest economically viable level. Combined with ultra-wide cutting headers, reaching record widths of up to 18 meters, and synchronized logistics systems, where grain carts run alongside the harvester to receive output without forcing the machine to stop for even a second, American harvesters can achieve throughput levels of around 70 tons per hour. This is the fundamental distinction from many European machines, such as those produced by Claas, which prioritize flexibility for smaller, fragmented fields, while American machines are engineered to dominate vast, open plains. The race in high-tech agriculture does not stop on the ground. The aerial front also clearly bears the imprint of the United States. With fixed-wing drones, American farmers have successfully monitored and sprayed vast megafarms spanning thousands of acres. Rather than relying on permanent infrastructure, these systems operate like mobile field units, deployed directly from mobile hangars positioned at the edge of the fields. The process begins with a reconnaissance phase. Flying at high altitude, multispectral sensors scan the entire area, allowing AI systems to construct digital maps and isolate pest and disease hotspots. This is followed immediately by the strike phase, in which drones autonomously return to treat precise target coordinates, instead of wasting chemicals through blanket spraying as in traditional methods. Crucially, traveling at speeds of 90 to 120 kilometers per hour, the long wingspan generates powerful downwash airflow that forces spray droplets through dense crop canopies, ensuring adhesion all the way down to the base of the plants. This mechanism not only reduces chemical usage by up to 60%, but also enables U.S. agricultural products to more easily meet the stringent residue limits imposed by the Food and Drug Administration. If vertical farming represents fully enclosed agricultural factories, then in cities like New York and Oakland, another revolution is unfolding at the very top of urban buildings. More than 500 farms are now greening industrial rooftops, an approach that transforms thousands of acres of abandoned concrete into productive systems, delivering yields up to 10 times higher than traditional farming. The greatest challenge in bringing agriculture to rooftops is structural load. To solve this, engineers eliminate natural soil entirely, replacing it with ultra-light engineered substrates, a blend of porous mineral aggregates and organic compost. This specialized structure allows a 30-centimeter growing layer to deliver maximum oxygen to plant roots, while keeping the total system weight to just 1/3 of conventional methods. Operationally, these farms function as a smart hybrid between soil-based cultivation and hydroponics. Nutrients are managed through fertigation technology, which injects organic nutrient solutions directly into drip irrigation networks. This enables vertical intercropping techniques, for example, planting fast-growing lettuce between rows of longer-cycle crops, such as cabbage. By optimizing every square inch of available space, a rooftop farm of just over 1 hectare in Brooklyn can supply up to 9 tons of food annually. More importantly, all produce is harvested and distributed the same day to nutritionally underserved neighborhoods, turning idle concrete rooftops into critical food security infrastructure. Fresh produce, however, represents only the visible layer of value. The deeper strategic benefit lies in urban regulation. By absorbing millions of liters of rainwater each year, these systems directly reduce pressure on municipal drainage networks and lower building temperatures by up to 5 degrees Celsius during summer months. For this reason, despite high upfront investment costs, the combined gains in energy efficiency and atmospheric control establish long-term value, transforming buildings from passive structures into active systems capable of self-regulation in the face of increasingly extreme climate conditions.